Thank you, everybody, for coming, and thank you very much for inviting me to give this talk and start this very interesting collaboration. So, yeah, I'm going to talk about high-throughput searches of topological materials, but since I'm not sure everybody knows what is a topological material or how can we look for them, I'm going to start from scratch. Okay. So this is the outline of the talk. I'm going to start with an introduction to topological materials, then how do we perform topological diagnosis, that we can do these high-throughput searches, because it was not easy at the beginning to diagnose topology, and for that, I'm going to introduce this very interesting tool, which is elementary band representation. Then I'm going to discuss the topological materials database, where we can find electronic band structures, magnetic materials, phonons, abstracted atomic limit, and also photonic crystals. I will discuss the applicability of the same method to heavy fermions, and then I want to discuss a little bit how can we, again, use this formalism to go beyond the single particle picture. So topological materials represent a revolution in quantum mechanics in a sense that they violate the original classification of matter that was done when Thomson discovered the electron. So as a function of the electronic current, the first classification was given in insulators, semiconductors, and metals. And why topological materials violate this classification is because within the same formalism, within the framework of the single particle picture, without the need of developing a sophisticated Hubbard-Hamiltonian, like in the case of other correlated materials, they are insulating in the bulk, but robust conductors at the surface. So they are semiconductors in the bulk, but at the surface we see these electronic channels that are very robust. And the reason is what I'm going to explain to you during this talk. But before that, I want to discuss the two types of insulators that we can find in condensed matter physics. So one is the band theory insulators, where they are given by electron counting. So we have conduction valence bands and conduction band, and by electron counting, we fill the last valence band, and then we have an energy window, and then the conduction band. And with this, we use the single particle picture, and it works very well. Whereas we also have correlated insulators, where by electron counting, we have a metallic phase. However, when we look at the experiments, it happens that in these let's say protected metals by electron counting, what we really have is an insulating gap. This is a mod gap, and it's given by the many-body wave function. And the way that we diagnose topology in this case and in this case is completely different. And one of the research lines that I'm trying to develop is the bridge between the formalism that we use for band theory insulators, try to apply it to correlated insulators. I'm going to start with the band theory insulators, and let's discuss the topological phases that we can find using the single particle picture. So there is a crossover between topology, symmetries, and dimensionality. So depending on what symmetries are present or absent, and the dimensions, we can have one topological phase or another one, and its topological phase has a different bulk boundary correspondence. So they are all insulating in the bulk, but we can have a polarized state in certain edges, or in every edge, or a surface state in every surface, or in some surfaces, depending on the symmetries. So we start with the very famous quantum Hall effect. That was the first topological order that was discovered by von Klitzing. So we all know that we apply a magnetic field at a very low temperature in a 2D narrow cap semiconductors, and we see this very robust edge state that is spin polarized. That we all know, but in terms of topological classification, to have this topological phase, we need time reversal symmetry to be broken, and it only exists, the quantization only exists in even dimensions. So we can have it in 2D and we can have it in 4D, but we will never measure the quantum Hall in 3D, for example. The material realization of the quantum Hall was introduced by Duncan Haldane, and it got him the Nobel Prize in 2016. And again, it's the realization of the same topological class. Time reversal symmetry needs to be broken, but in this case, it's not broken by an external magnetic field, but by intrinsic magnetism. But it's in the same case, they only exist in even dimensions. And it was many years before a new topological phase was found, and when this new topological phase was found, it happened the first realization in a material, and it's the quantum spin Hall. And the quantum spin Hall is like two copies of the quantum Hall effect, one for a spin up and another one for a spin down, but in order to keep them together, time reversal symmetry needs to be preserved. And instead of having one edge state, we'll have two helical edges, one for a spin up and a spin down, or positive and negative spin, because one time reversal symmetry is preserved, we don't really know what the spin is doing. We need a strong spin-orbit coupling. I mean, the spin-orbit coupling is needed, not in these two cases, and it exists in 2D and 3D dimensions. In 3D dimensions, we have the 3D topological insulators, and in this case, we find a surface state in every surface of our material. And same with the 2D version, we have an edge state, this helical edge state in every edge, is not the case here. And the last example I want to show you is the topological phase protected by mirror, by crystalline symmetries. So this was introduced by Bernevik and Liang Fu in 2011, and what happens here is that we have a topological phase protected by a crystalline symmetry of our crystal, and the surface state will only exist in the surfaces where the symmetry is preserved. So different topological phases give different surface properties. So why are topological insulators so interesting? They are very interesting because they have these very robust edge and surface states, and we can think about many potential applications, since in principle they are independent of size, temperature, and weak disorder. So if we look at transport properties, we have quantum anomalous Hall, spin Hall, Nernst effect, nonlinear optical transport, magnetotransport that can help to develop environmentally friendly technology. They can also be used for energy conversion, like photovoltaic or catalysis. When we combine chirality plus topology, we can use it for dark matter detectors, for example. And if we go to the superconducting state, they present these non-abelian anyons that perform this braiding that can be used for quantum computers. So they are potential platforms for application in many areas of condensed matter, but what we need to find is a suitable material. Okay, so all these fascinating properties, there's these very robust surface states and these strange abelian statistics happen because of a magnitude that was forgotten at the beginning of the century, which is the very phase. So the very phase was completely missed by all these great minds of that develop quantum mechanics. And it's related to the fact that quantum mechanics allows for an ambiguity in the phase, right? You can choose your phase, you can make a gauge transformation, and the quantity that we want to measure is going to be gauge invariant. Our observable will not change. So this geometrical phase was ignored because if the path is open, you make a gauge transformation, you get rid of it, and it doesn't matter. However, if we get our wave function and we perform a closed loop, it happens that this geometrical phase that we add might prevail. And it might become gauge invariant. And if it becomes gauge invariant, we can measure it. It's not a very complicated concept when you learn how it works, but it's subtle in a sense that this is why it was missed. And there was some feeling about this phase with the Aharonov-Bohm effect, for example. The Aharonov-Bohm effect, actually, this interference is given by the very phase. But it wasn't in 1984 when Michael Berry put this nominal phase with this nominal paper and explained everything. So what is the physical signature? The physical signature is in transport. it's not local, it's non-local. I mean, topology is a global property. So if we integrate the very phase over this closed loop, what we get, for example, is the Hall conductivity. The integral of the very phase gives us a topological invariant. In this case, is the Chern number. This is what is related to the very phase. And this is what gives us the quantization of the Hall conductivity. So the very phase is what is the main physical magnitude related to topology. And when we integrate it, we get transport properties that are very robust and symmetry protected. All right, so calculating the very phase is not an easy task because we need to go to reciprocal space. It's in the Brillouin zone where we find these closed surfaces. And then we need to integrate the very connection, which is not easy either in ab initio codes. Now it's more doable, but at the beginning it was like, there were many problems with the random phases we get in ab initio codes. So performing a high throughput calculation was not straightforward because it was very time consuming, and also you need to calculate the very phase in every surface. And there was not like hints on where topology could exist or not. This is what it was considered very exotic. A solution came from Kane and Melle when they thought that okay, if we have two insulating phases and one is topological and the other one is not, there must be a phase transition. And within the single particle picture, a phase transition is always given by closing the gap and reopening it again. And so they choose the most simple symmetry we find in crystal, which is inversion. And they thought that if we have a phase transition, it must be seen in the band structure. So whenever we have a band inversion means that we have a topological transition, and the way of calculating this topological transition was by multiplying the eigenvalues of the inversion symmetry. So if the product of the eigenvalues is odd, means that there has been an inverted band. If it's even, means that we have a trivial phase. And we only need to do it in the high symmetry points, so the calculation was actually completely reduced to just looking at the high symmetry points, some high symmetry points in the band structure. However, this was only done for one symmetry, and we have many symmetries in our crystals. And what I want to explain you too is what's the meaning of this band inversion in real space. So for that, there are two concepts that I need to share. One is the atomic limit. So the atomic limit is what in my community we refer to trivial topological phases. And a trivial topological phase happens when we look at the charge in real space. So if we ask about the charge in reciprocal space, there's nothing we can say because the block states are spanned in the full Brillouin zone. But if we calculate the Vanier states and we integrate to real space, we get the Vanier functions. Vanier functions have a Vanier center where the charge is localized, and we have a trivial phase when the Vanier center is maximally localized in the atomic site. So if our Vanier center is maximally localized in the atomic site and preserves all the symmetries of the crystal, we'll have a trivial phase. If this is not happening, so it's not maximally localized, it's somewhere else, this is a bit exaggerated, and we have an insulating phase, our gap, our bands are going to be non-trivial. So Vanier states give us, and this can be proved also mathematically, give us actually the shape of the Vanier states, tell us whether our phase is going to be, our insulating phase is going to be trivial or topological. Okay. And the second concept or tool that I'm going to use is an elementary band representation. So an elementary band representations were introduced by Zach and Michel. In the next slide, I will show you the references. And it was because Zach really wanted to understand band structure to a philosophical point. I mean, he really wanted to see what's the essence of band structures, and he wanted to find the center of mass of the bands. And by trying to explore these ideas, he came up with the elementary band representations. So elementary band representation is a connection between real space and reciprocal space without solving any Hamiltonian within the single particle picture. And it's a set of bands that are described by three ingredients in real space, which is the orbitals, the Bykov position. In the case of the Honiton lattice, is the 2B, is these blue dots, and the lattice, which is the hexagonal lattice. Or more technically, is the irreducible representation of the side symmetry group, the Bykov position, and the space group. So, but more or less is orbital, side, and lattice. So with these three ingredients, I can tell you the reducible representation, I mean the traces of the symmetries of the wave function in reciprocal space. And it's unique. So I can tell you this gamma 1, gamma 4, K3, M1, M4, just by these three ingredients. And instead of having PC orbitals, I have Px and Py. I cannot disentangle them because they transform into the other one. I'm going to have a different set of bands with a different dimension. I mean, here we'll have 2, but here we'll have 4. Without the spin-orbit coupling, it will have added spin-orbit coupling. Here we'll have 4, and here we'll have 8. And I can tell you, this should be here, again, the reducible representation at the high symmetry points, and this is all tabulated, and it's known. So why is this related to topology? It's related because an atomic limit, a set of bands that actually can be Verniorized, is given by elementary band representation. So these three ingredients actually define a Vanier basis, and this Vanier basis can be maximally localized. So the relation with topology and elementary band representation is given by this paper by Zach and Michel, because what they say is that if we have an elementary band representation, these three ingredients that have to be really minimal, we cannot disentangle them, then the bands in reciprocal space, they have to be connected, okay? And an elementary band representation, as I told you, describe an atomic limit. And this is the case only if our bands are trivial, because if they are not trivial, then the set of bands described and tabulated by Michel and Zach are not going to be connected, and they are going to be topological. And this method actually works for every symmetry in every space group, not only inversion symmetry. So by using this elementary band representation, which is basically considering the irreducible representation of high symmetry points of every crystalline symmetry of every space group, of every material, we can actually diagnose topology in a fast way. So we have our lattice. We have our lattice. If we can find a Vanier basis given by these EBRs, by this elementary band representation that is maximally localized, our bands are going to be connected, which means that the charge is localized in the atomic side. On the contrary, if this doesn't happen, our bands are going to be disconnected, which means that the charge is not localized in real space. So what we do when we do calculations is the opposite. First, we calculate just the wave function at the high symmetry points. We calculate the irreps, and then we can tell what is happening in real space. But it's very efficient and it's very fast. And so now, if we want to look at the topology of any band of any material, we just need to calculate the irreps at the high symmetry points, which is given by the traces of the symmetry operators. So instead of doing these calculations of the Wilson loop, we just need this information. Okay, so we develop an algorithm to actually perform these high throughput calculations. In this case, we did it with VASP because we had many codes interfacing VASP at the time, but now we have the codes also interfacing Quantum Espresso and Vanier 90. So we have VASP. We have the organic crystal structure database from Karlsruhe. So we calculate the wave function at the high symmetry points by several homemade codes. in a matter of 10 minutes, we can tell whether our material is topological or not. And at the beginning, this was only done at the Fermi level, because it's what experimentalists are interested in the transport regime. But it happens that the very phase can be anywhere in the band spectrum, not only at the Fermi level. So since we needed to calculate all the bands anyway, we decided to do the analysis for every band in the energy band spectrum. So what happens sometimes, and this we call repeated topology, is that maybe at the Fermi level your bands are trivial, but a few MeV below, or yeah, something like that, you can have a topological gap. And this is very interesting because by doping or gating or whatever, you can reach this topological gap. Or it also happens that we have materials where all the bands are topological, like the case of bismuth, because it has a very strong spin-orbit coupling, so all bands are split. And this is an illustrative example of bismuth to magnesium 3, where it was reported to have a topological gap, and this we can see. And then they said there was a resonance before the Fermi level. And well, if we do the analysis, actually this resonance is also this supposed resonance that we find at the surface actually comes from a topological gap. So it happens that this thing here is a topological surface state, and if we go 1 eV below, we have another topological gap, so we have another topological surface state. So this means that the very phase is a fundamental magnitude of band theory that should be taken into account, because actually it's more present than what we thought. Topological materials are not something exotic and rare. They are actually more common than what we thought. So this is the analysis of the topology at the Fermi level. So the orange is non-topological materials. The blue are topological metals, and the green ones are the topological insulating phase. So it's actually the amount of topological materials we can see is very important, and it's, as I said, a fundamental property of the band theory. So at least within, of course, DFT and the pseudo-potential we are using, and with all the flaws and amperes that DFT has, but still we found that 50% of the materials in the Karlsruhe have topological properties, and if we look at the Fermi level, and if we look at the full band spectrum, we see that 80% of the material has at least one topological gap. So this is very interesting, and it's good news because it means that we also have a lot of room to find a suitable topological material. Another phase that came from these searches is what we call the abstracted atomic insulators. So this phase is not topological, but it's not trivial either, because it has surface state that are dictated by symmetry, and they come from the bulk. And we can predict them just by looking at the bulk, but then they don't have the topological protection. So what I mean is the following. Imagine that we have a lattice, and we have the Wannier centers localized in the atomic site. As I said, this is trivial, but it could happen that the charge has moved away from the atomic site and localized somewhere else in the crystal, but this charge is maximally localized. It's related to the covalent bonding. So it's not topological because the charge is maximally localized, but somewhere else. However, if we want to go from this phase to this phase, we need to close a gap, because the symmetry of the bands is going to change. It's going to be a different elementary band representation. And whenever we cleave this crystal, we are going to find some charge localized at the surface. And this happens, for example, in many materials. This is the case of cadmium antimony. So these are the cadmium and antimony atoms. And this is the charge. Some orbitals have moved away from the atomic site. So even though in the bulk we have an insulating phase, if we cleave it by different planes, we're going to find very interesting surface states in a very large gap. So abstracted atomic insulators belong to trivial classification to the orange color that I mentioned before, but they are not fully trivial. They have these interesting surface states, and yeah, okay. So we also apply this formalism to magnetic materials, and the problem with magnetic materials is that they do not accept a Vernier representation if we use the orbitals that the sp and d orbitals that we use for the previous case. However, if we can define magnetic orbitals, orbitals that have time reversal symmetry broken, then they do accept a Vernier representation. So we did that. We generate the elementary band representation based on these magnetic orbitals and develop all the tables. And well, we found also a bunch of new topological magnetic materials. So in this case, there were some shortcomings. First, they are not magnetic materials database as they are for non-magnetic ones, because in order to be sure that your magnetic structure is correct, you need to do neutron scattering, and it's complicated. So, so that was a problem. The magnetic databases that we found had very few magnetic materials of the order of 1,000, 2,000. Then, of course, DFT doesn't work well with correlations, so we did calculations for different values of U and different values of J, and sometimes depending on the U, the topology might change, but still as a starting point we found all these materials that for certain values of U where the experimental magnetic moment is not different from the one we calculated, they display topological phases. Another interesting case are the heavy fermions. So the Fermi fermions, both the Kondo systems or the mixed valent, are given by a set of F bands that are cut by a D band that is very dispersive. And if the E-reps of the band is different, what happens is that we get a lot of gaps. So if we get a lot of gaps, and considering how common it is to find the very phase in our band spectrum, this calls for a topological, for an EBR, elementary band representation analysis. Why? Because, as I said before, we have topology in all the spectrum of the gap, and if we find a gap that is topological below the Fermi level, for example this one, unless we find another gap that is topological with the opposite invariant, the topology is gonna kept in every gap that goes up. It's what we call cumulative topology. So in this case, with so many gaps, cumulative topology was probably gonna be a very important thing, and analyzing these band structures was also very interesting. It's heavy fermions. Of course, it's more tricky because we have multiplets and singlets, but it happens that depending on the filling of our material, we could actually apply the single particle picture because the symmetry of the multiplets, it happens that has the same symmetry as our single particle picture. And this is the case of samarium hexaboride, who has these 5d and 4f electrons very close. This is why it's mixed valent, because it's an oscillating between 5f and 5,6. And because of the electron counting, we have that the filling of the bands is half filling minus 2. And half filling minus 2 corresponds to actually J equal to L plus minus 1/2. And the symmetry of the bands is actually the same as we find in our orbitals. So because of this feature, and also because the finding energy are very close to this JL plus minus 1, because of this feature, we can actually apply the single particle picture. So this is what we did. We applied the single particle picture, and it happens that in samarium hexaboride, we do have a topological gap at the Fermi level, but we also have a topological gap right below the Fermi level. And it's given by a mirror chair number. We develop a model and calculate the winding of the Wilson loop to be sure that everything was right. But what is very interesting here is that these topological gaps, the origin is not at the Fermi level, neither below the Fermi level. It really comes from the from deep in the band structure from the borite. It's actually not even given by samarium. Okay, and this will hopefully appear soon in arXiv. And okay, so we did these high throughput searches, and we find many materials, magnetic, non-magnetic. We are also doing now heavy fermions, but we also found different topological phases by themselves, like the high order TIs, where the bulk boundary correspondence is not bulk surface, but is bulk hinge. The fragile phases that I did not explain, but is the topological phase of the twisted bilayer graphene. The abstracted atomic insulators that I told you, and in the magnetic cases, we found many possible action insulators. So action insulators are high-order TIs that happens in magnetic materials, and we see very interesting hinges depending on the symmetry. You can have 1, 2, or multiple hinges, or hinges in every corner. So all this has been allowed in this topological quantum chemistry database that we discussed before, and this is why I'm here, where you can find information about the band structure, electron number, topology, etc. But this is not unique of fermions. We can also apply it to bosonic systems like the phonons, and it works exactly in the same way. Thankfully, there are several phonon databases, like the one at the University of Kyoto and the one in the materials project, so there was no need to do the calculations. In the other case, we had to do the calculations because the materials project didn't have the spin-orbit coupling included. And this is very important for topological diagnosis. But for phonons, it's not important. So developing similar, let's say, algorithm as the ones for our electrons, we calculated also the topological phases in phononic materials. And there are topological phonons. I mean, it's not that phonons in topological materials, but topological phonons by themselves that also displayed the same bulk boundary correspondence. So if we have a topological gap, we're going to have some surface states. And we can also do it for photonic crystals. Photonic crystals can accept a block representation within the Maxwell equation. And in the same time, we can calculate the irreps at the high symmetry points of dielectric rods, and it also works very well. And we have, there is not a photonic crystal database, but we have applied it for several candidates. In the Bilbao crystallographic server, one can find all the tables and irreps and information about the group theory. And the codes that we use are publicly available. One is written in Fortran, it's in the Bilbao crystallographic server, and the other one is a Python package that is called irrep, and one can download it from here. So, so far so good. But something interesting happened when we were looking at topological metals, like the one I show you here or here. You see this crossing is, no, this one here is 8-fold, is topologically protected. It might have, is the folding of two Rarita Swinger fermions, and it's quite isolated. So when we were doing these high throughput searches, we also were looking at ideal materials for experimental applications. So we found this one, and it was very interesting because it's a set of isolated bands with these crossings, and this other one which is azurite. Well, what happens is that these protected metals, when we use more sophisticated codes, or like DMFT, or we look at experimental data, in the end they are insulators, they are Mott insulators. And the question that arises is that, okay, so this that should be a protected metal, then it's an insulator. but is this gap special from one that has an insulating phase already with a single particle picture, or they are exactly the same type of gap? So trying to answer this question, we decided to go beyond the single particle picture, but trying to apply the same crystalline symmetries formalism. But also because this is a very interesting article from Quantum Magazine that actually shows all the topological zoo, all the topological phases that one can find. And actually, topological insulators are right here. There are many exciting phases happening beyond this little window here. And because for the materials within the single particle picture, the gap can only be open owing to spin-orbit coupling. And spin-orbit coupling doesn't go beyond 300 MeV, so this is going to be a problem for applications because the gap is very small. So I'm going to just pop some ideas about how to deal with this case. The case where we start with a protected metal and then we have a gap. Is this gap trivial? Is it topological? What can this gap tell us? Or is there a chance that we can find a TI that has a large gap, or is fundamentally not possible for whatever reason? So for that, we're gonna use a simple model with crystalline symmetries because we need crystalline symmetries to apply this method, and we're gonna use Green's function. So the model is this diamond chain, and is described by this Hamiltonian, and we add correlations through a how are you, but we don't want to break any symmetry. It's not a mode transition because we break the reversal symmetry, it's a mode transition because of correlation, keeping all the crystalline and time reversal symmetry with us. So we have three hoop-ins that are T2 is in the intracell between next nearest neighbors, T3 is hoop in the diamonds, and T1 is for nearest neighbors. And depending what is the dominant hoop-in, what we see is that we might find different phases. So if the dominant hoop-in is T2, this is a trivial SSH where the charge is localized inside. If the dominant hoop-in is T3, we're going to have an obstructed atomic limit because the charge has moved away from the cell and is outside the cell. And if the dominant hoop-in is T1, we're going to find a metal. We're going to find a metal because we're find all these states are degenerate and the Hamiltonian is in a half filling regime. Okay, so we develop a tight binding model. This is the phase diagram within the single particle picture for the different hoop-ins. Now we are here. We develop a tight binding model with and calculated the irreps. And actually, by using the formalism I told you before, it's an atomic insulators. Here we have the Fermi level. And we can write the many-body wave function as a product state of its diamond. So its diamond can be defined by one of these operators, and it's a product state of its diamond, and they all transform under the same irrep or the same symmetries. If we go to the case where T3 is dominant and the charge is outside the cell, we find an, as I said, obstructed atomic limit because we're going to have some charge localized outside the cell. We develop a tight binding Hamiltonian again. We calculated the irrep, and actually we get what we expected. And we can also define these operators here. And the metallic phase is the most interesting phase because we develop a tight binding model, and in the half filling regime we have this very flat band crossed by another flat. They are the same irrep, so we don't get the gap, but we were interested in this phase because to see whether if we add how are you, we could get an insulating phase. And the inspiration comes from this paper of Yao and Givelson from 2010, where they actually they analyzed a lattice without coupling it, its lattice separately, but they found, they proposed very interesting things. So actually our diamond chain is the 1D case connected of this lattice presented by Givelson. So why is this lattice interesting? This lattice is interesting because you can describe the Hamiltonian with two Hopins, and within the single particle picture, what they prove is that if I have my many-body wave function, I can describe it as a product of the Kram's pairs because then reversal symmetry is preserved, and the point group of my square, because there is no translation, but in the end is the E-rep that describes my side symmetry group. If we apply to my wave function, it needs to transform even, which means that if I apply to my wave functions, I need to get my wave function. Okay? So what happens when we add correlations? When we add correlations, and if we plot the phase diagram as a function of u, what we get is that we find two phases. One was called phi s because the wave function transforms as an s orbital, and if we apply the C4b, which is the point group of the lattice, we get the wave function again. But then he found another phase, and the other phase had the symmetry of the dxy minus iy d orbital. And actually, if we apply our point group to this many-body wave function, it transforms odd. So this phase and this phase are different, even though there is no symmetry broken. It's just depending on the couplings, you have the symmetry of the s orbital or you have the symmetry of the d orbital. So we already found different phases as a function of u, and this inspired us to actually look for the diamond phase and actually define an invariant. So using density matrix renormalization group and quantum Monte Carlo, we calculated the exact, we calculated the phase diagram to make sure that we actually get an insulating phase where we expected to get an insulating phase, and this is what happened. And then by applying this mirror symmetry, which is the one driving the transition, we see that this mirror symmetry applied to the many-body wave function of this side transform even. So we have different topological phases. One of them, different phases, one of them appears when we add u, and it actually has a different invariant. So at least we found a case where a metallic phase by single particle by mean field has a different transformation when we add correlations. And then we also found a way to actually distinguish these two phases too. Okay, so how can we calculate this in a, let's say, in beyond the DMRG, because DMRG and these codes are dimension dependent, and if you want to go to 2D, it's already super difficult. So we use the topological Hamiltonian and the Green's function. So if we calculate the Green's function using the cluster perturbation theory, as we did in this paper, for frequency, zero frequency, we can get the topological Hamiltonian, and once we have the topological Hamiltonian that is Hermitian, we can actually apply this topological quantum chemistry and EVR formalism. So for the first case, the atomic phase, it works very well. We get, with the Green's function, the Hubbard bands, and then, okay, for the first two cases, it works very well. However, yes, I think I removed 2 slides to not make it very long. When we go to the mod phase, which is the one that we are interested in, what happens is that if we go to the mod insulating phase, with the Green's function, we get the Hubbard bands, and this is very interesting because we get the correct gap. But of course, then we have a problem, and the problem is that the self-energy diverges, so we cannot get the single particle wave function because it's 0. So we cannot analyze it. So whenever we get to this phase, what can we do? And one proposal is to go to the two-body Green's function. So if we go to the two-body Green's function, under certain constraints, and well, the paper is here, I don't want to explain everything. Under certain constraints, we actually can apply the eigenvalues analysis and diagnose the mode phase that I told you before. So there is a very interesting research line based on the application of this methodology to Green's function and actually be able to diagnose topology in correlated materials and maybe find new correlated phases. So within band topology, I show you the high throughput searches, and I think we have understood band topology very deeply by now, and there is more topology in nature than expected. And about correlations, well, we can apply to some feelings of heavy fermion systems, and we find interesting phases when we add a Haber-U to protected metal phases, but I mean, there is a lot of progress still to be done, and eventually it will be nice to be able to use Green's function to diagnose topology in materials. And I thank everybody of people I work with and you for your attention.